Welcome back to my channel. Dear students, today I am going to talk about the VLSI and chip design. So, in which I am going to put the 5 videos, each video from each unit. So, this is the 23 regulation syllabus VLSI and chip design. So, in which I am going to talk about the first unit. So, that is the unit 1 MOS transistor principles. So, this unit consists of the fabrication process along with VLSI design flow, review of MOS transistors, CMOS inverters, DC characteristics of CMOS inverter, ideal and non-ideal IV characteristics, MOSFET transistor characteristics under static and dynamic conditions, technology scaling, logic effort, stick and layout diagrams. So in this video, I specifically explain about non-ideal IV characteristics. So this is a non-ideal IV characteristics. So usually the IV characteristics is representing about the characteristics features between the current and the voltage of a particular transistor. So in this case, in theoretical, we can say that transistors are having ideal characteristics. But as well as the practical, the transistors does not have the ideal IV characteristics. Meanwhile, the characteristics variation from the ideal characteristics, that is said to be as a non-ideal IV effects. Due to some of the things, the characteristics may be varying. So what are the things that making the characteristics to be varying from ideal IV effects are velocity saturation, mobility degradation, channel length modulation, body effect, subthreshold condition, Johnson leakage, tunneling, temperature dependence, and geometry dependence. So these all are the things that which makes the transistor to be in unideal condition, that is non-ideal condition. So here, what are the things these particular parameters are doing? Velocity saturation and mobility degradation is the first thing. Yeah, at high lateral speed, what is meant by velocity saturation? Actually, the velocity is nothing but about the speed per time. That is how much the current is moving for a particular second. That is the velocity, and it is getting rest. That is about the saturation. So, as we discussed earlier, you know that there were three regions in the VLSI design, particularly in the mass transistor principle. They are the cutoff region, active region, and the saturation region. And here, in this, the velocity saturation means that they are getting rest. At high lateral field strength, the velocity ceases to increase linearly with the field strength. This is called velocity saturation. This is lesser IDS than the expected at high VDS. IDS means the current moving between the drain and the source, and VDS means it between the voltage between the drain and the source. So always at the high VDS, the current is lesser than what we have expected. This is called velocity is getting saturated. And what about the mobility degradation? The mobility degradation means that degradation is the process of reducing its strength. In this case, the mobility means that when the charge carriers are moving from one place to another place, that is from source to the drain, the movement is getting faster as much as possible, and as soon as it attains its maximum value, it is getting degraded. So this is called mobility degradation. At high vertical field strength, the carrier scatters more often against the surface and reduces the carrier mobility. So this leads to less current than the expected high VGS. VGS means the current flow, the voltage flow between the gate and the source. The next one is the channel length modulation. So the channel length modulation means that the channel is created between the source and the drain whenever the biasing is attained at the gate terminal. So the channel is formed in the form of a charge carriers. Here, as we know that the charge carriers are moving in a single row like a single path in a theoretical logic, but as per the practical logic, it is not like that. it is getting deviated or distracted due to the high VDS. Whenever the voltage at the drain of the source is getting maximum, it increases the sizes of the depletion region around the drain and thus effectively shortens the channel to L effective. So the increasing in the size of the depletion region is getting reduces the length of the channel, which is represented as a L effective, which is equivalent to the L minus LD. L is the actual length of the channel, whereas the LD is the channel at the drain due to the depletion. So this is what the channel length modulation. Then the body effect. This is an important 2 mark question as far as the VLSI design is considered. For every end semester examination, this question would be asked usually. So what is meant by body effect? Actually, what is this body? This body is the fourth terminal of the transistor. As we know, we are familiar with the three terminals. They are source, drain, and gate. But there is a fourth terminal that is known as body. Otherwise, it is said to be as a substrate. So this is the fourth transistor terminal. The potential difference between the source and the body affects the threshold voltage called body effect. So whenever the potential difference is applying between the source and the body, it would affect the threshold voltage. For example, the transistor will be active at the particular voltage, that is zero point 0.7 voltage as far as the silicon and zero point 0.4 voltage as far as the germanium is considered. This is called the threshold voltage. But the increasing in the potential differences between the source and the body, that is VSB, will affect the threshold voltage. So the entire substrate is getting affected. This is called body effect. So here this VSB affects the charge required to invert the channel. Increasing or decreasing increases the threshold voltage. Then subthreshold leakage. Subthreshold leakage means that the leakage in the charge carrier, the leakage of charge carriers in the particular threshold point, that is called subthreshold leakage. So you know that in practical, the leakage is definitely occurring whenever the charge carrier is moving between the transistors. So this could not be avoided, and when you compare with the theoretical concept, there is no concept like a subthreshold leakage. So you know that whenever the input is given, the charge carriers are moving between the source and the destination. Okay. So this subthreshold leakage means that during a transistor in off condition also, the current flow occurs due to several sources of leakages. So during the transistor is in off condition. Usually when the transistor is on condition, the charge carriers are moving from one end to another end. But as far as this subthreshold leakage is considered, it would be worked when the transistor is in off condition also. Due to the several sources of leakages, at VGS less than VT, the current drops off exponentially rather than abruptly becoming zero. This is called sub-threshold condition. VGS less than VT means that the voltage is very very minimum voltage. Already the threshold voltage itself is very minute, that is about zero point 0.7. But when you compare with the threshold voltage, this gate to source voltage is very low voltage. That is the input voltage. When the input voltage is lesser than the threshold voltage, that is at the beginning stage of the transistor, before the switches are on, when it is in the off condition, there are several leakages are happening. That leakages are said to be as a subthreshold leakage. This is called subthreshold condition. The junction leakage. Junction in the sense it means that the point, the terminals are meeting at a particular point. For example, the sources, the gate are meeting at a particular point. Similarly, the gate and the drain are meeting at a particular point. So these are said to be as a junction leakage. The source and the drain diffusions are reverse bias, which experience junction leakage into the well or substrate. The reverse biased PN junctions have some leakage, ordinary diode leakage, band to band tunneling, tunneling across heavily doped PN junction, sidewall between the drain and the channel, then gate induced drain leakage. So this gate induced drain leakage is another thing that causes the non-ideal IV effect. It occurs at the overlapping between the gate and the drain terminal. Most pronounced when the drain is at the VDD, the gate is at the negative voltage. Fats effort to reduce subthreshold leakage using a negative gate voltage. The next one is the tunneling or a gate leakage You know what is meant by tunneling? It is just like like a cave, or which means that something is penetrated into the substrate. It means that current into the gate, that is initially the gate current is zero ideally, but the thickness of the gate actually reduces a smaller number of atomic layers. Thus, the electrons are tunneling into the gate as causes some gate current. So, which means that the current is very minute when compared to the actual, but even though it is off, or it is in ideal condition, it is in zero. There are some of the electrons are moving, or some of the carriers are moving towards the substrate that causes the gate current. The next one is the temperature dependence. Both mobility and threshold voltages decreases with rising temperature. So during the temperature is getting increasing, keep on increasing, the mobility and the threshold voltages are getting decreasing. So the mobility affects the reduces IDS and high temperature. IDS is about the output current and the high temperature for on transistor, and similarly threshold effect increases leakage current and high temperature for off transistor. Reducing mobility is increasing at the time of temperature, and also reduces the threshold voltage. The last one is about the geometry dependence. So it means that the geometrically the length and the width of the particular terminals are getting affected, and this is because of this non-ideal IV effect. This causes non-ideal IV effects. So what are the two things, that is the length and the width? Length effective and the, as well as the width effective. Effective length and width. Then length and width drawn by a designer, actual dimensions. Long transistors experience less channel annihilation. So these all are the some of the points that would have been covered under the non-ideal IV effects. Hope you have understand the topic. If you not having any, mm, if you don't understand anything, or if you want some clarification, please be free to text me or put in the comment box, so I can easily explain over it within a few hours. So thank you for watching the video. Have a nice day. Hope I'll be seeing you in another video, that is from the unit 2. So thank you all.